Okay, so the first question is ballistic pendulum, and this hopefully, as you're looking at the past exam, you got the sense that this does follow. How do I- So this is your exact setup for the ballistic pendulum lab, and I'm hoping some of this will look familiar, and um, uh, it doesn't look surprising. All right, so consider the ballistic pendulum shown on right. The spring in the launcher is compressed, and when it released, it launches a ball of mass m. Let me just highlight some of the information that's given into a catcher of mass big M with a styrofoam cushion. That's your lab. The steel ball is embedded into catcher, and the ball catcher and the ball swings up to some height. You've seen all that. I guess this part A is something that you haven't seen. For our lab, we kind of skipped this part of the description, but okay, you know about conservation of energy, and you know about spring potential energy, so you should be able to do this. It's telling you the spring constant, and it's asking you for the launch speed V naught, assuming that the spring was initially compressed by some amount. All right, it seems so. Um, so this is where I want you to recognize that this is a conservation of energy problem, and be able to make kind of reasonable assumptions, like the fact that this launcher is all fixed down. So as the ball is launched, the launcher won't move. And that means that energy is conserved, but momentum won't be conserved because this the part of the fixture that fixes down the launcher will be applying on external force, so momentum won't be conserved. So hopefully all this um, isn't confusing. But so I'm saying all this out loud because the very first step in applying conservation law strategy, especially now that you know more than one conserved quantity, you know three conserved quantities: energy, linear momentum, and angular momentum. It's important that you identify conserved quantities. And depending on the question or the setup, there could be more than one conserved quantity, or like in this question, there could be just only one conserved quantity. So here, energy is conserved, and let's set up the equation involving energy conservation and see if we have enough number of equations as unknowns. So we write down conservation of energy. Then all the conservation law strategies follow the same step. You identify the snapshots that will be useful. So you have this snapshot here where the spring is compressed by this amount. So I'm gonna call this my initial. And here's another snapshot at the moment where the ball is about to be fired. And so here the displacement will be 0 and the ball has some speed of V naught. And let me call this snapshot, well, final. So at these two snapshots, you write down the expression for the conserved quantity. And the quantity being conserved means that it doesn't change. So I can say the initial potential energy, or the potential energy at the snapshot I, plus the initial kinetic energy is equal to the final potential energy and the final kinetic energy. And I'm writing down some of these knowing that there will be 0. I like to write them down just so that I don't make mistakes. It's easy to write it down and then recognize that initially before the ball is released, it's not moving, so initial kinetic energy is 0. And you can identify here that as the ball is fired, the spring is all back to equilibrium length, so the spring potential energy should be 0. So I am crossing it out, but it's good to start out with those expressions written in so that you don't accidentally forget something. So with those simplifications, then I can write down more specific expression. The initial potential energy should be the spring potential energy, 1/2 K displacement delta x squared is equal to the final kinetic energy, which is given by this speed here, 1/2 the mass of the still ball times V naught squared. So that's your starting point, and I think most people in the class can do the algebra. So let me just write down the final answer here. When you solve for V, the final speed, or I guess the initial, the launch speed of the ball is equal to square root of k over m times delta x. And if you want, and if you have the time during the exam, you can do dimensional analysis to make sure that the units work out. But there's the speed. Okay, let's keep going. So, so for the rest of this question, I'll just highlight the starting point. I want, especially since you have a detailed solution already in the exam review module, I'll try to reserve more of the time for the other questions. So it says now imagine the ball is launched and embedded in the catcher. To what height h does the still ball catcher assembly rise? So this is exactly the same setup as your ballistic pendulum lab. And what I want you to remember is that neither the energy nor the momentum is conserved from the very beginning step to the final step of the catcher rising. So these are the kind of snapshots that you have to be thinking about. There's the snapshot 1 where the ball is moving to right at speed of V naught. The catcher is at rest. And then there's the snapshot 2, which is the snapshot taken when the collision has taken place, and now the ball is embedded into the catcher, and they're both moving together at let me call that speed, I guess just the V. They're moving together speed of V, and the ballistic, the catcher is still hanging from the ceiling or the holder. That's the second snapshot. And the third and the final snapshot is where the catcher has swung up to some height, and you can measure the maximum height h, and that's the third and the final snapshot, which should relate this height to the other quantities given in the question. And what I want you to remember is that throughout these processes, some of the 3 conserved quantities won't be conserved. So the angular momentum here isn't really involved at all, so let's forget that. So there's energy and momentum as potentially conserved quantities here. And I hope as you look at these processes, you can recognize which quantities are not conserved. So going from snapshot 1 to 2, you should be able to see that energy is not conserved. And the main thing that you should look at to recognize that is the description of the collision, where the ball gets embedded into the catcher, and from that description, you should recognize that this is what your textbook calls perfectly inelastic collision. Or the phrase I actually like better is, rather than perfectly, I like the phrase completely inelastic collision. But either way, the key phrase here is that it's an inelastic collision. It is where 2 things stick together. In collision like that, there's no way that kinetic energy can be conserved. And you can work that all out, but for the purpose of this question, it's important that you recognize the fact that energy is not conserved. And from snapshot 2 to 3, you should recognize that momentum cannot be conserved here. And here, I guess the easiest to way to see that is to see that, well, that the final momentum is zero and the initial momentum isn't zero, so I guess it can be conserved. That's one way to see it, and that's fine if that's how you're looking at it. And the reason here has to do with there's an external force of tension that that imparts impulse to the catcher assembly, and over the duration of time, and as this swings up, momentum is simply not conserved. So that's the most important thing that you have to recognize. And once you've done that, then the rest is well, it's easier. It's an application of conservation law strategy. So you look at going from step 1 to 2. So here you are going to be using conservation of momentum. So you write out the total initial momentum is equal to total final momentum, or initial and final referring to steps, snapshots 1 and 2. So in snapshot 1, only the ball has momentum, so it's going to be mv naught plus 0 if you want to spell out that the catcher doesn't have momentum. And for the final momentum, you can treat this as one object. So say that the ball plus the catcher has some speed v, and this is the expression that says my momentum, the total momentum is conserved. That's one equation. And the snapshot from 2 to 3, you should do that separately, since different quantities are conserved here. And here, what's conserved is total energy. And you can see that you have the situation where kinetic energy is going into potential energy through this change in height. So you write that out. So initial kinetic energy plus, and I, once again, like to write this out so that I don't forget anything, equals final kinetic energy plus the final potential energy. So the final kinetic energy should be 0, because at the highest height, the velocity of the assembly should be 0, otherwise it won't be at the highest height. And to set the initial potential energy to be equal to 0, you are basically defining your reference point. Say that y is equal to 0 here, so you'll define this point, where the cart is starting from, to define that to have 0 potential energy. If you don't do that, then you are basically writing in terms of the difference in potential energy, which is physically meaningful, and you can do it that way too. So with that, you write out the what the actual expression is. The initial kinetic energy is 1/2 the mass. Make sure to remember it's the total mass times the speed squared is equal to, at the height h, it is gravitational potential energy m plus big M g times h. And so it looks like the question is asking for height h. So this is one of your unknowns. And you worked out V naught earlier. So V naught is not an unknown, that's known. Good. So it looks like you don't know V, so you need to solve for V. So you have two unknowns. This V here is the same V as the V in the second equation. So you have two unknowns, two equations. You should be able to solve it. The rest is the algebra going through the first and the second equation and working out what H is. I guess eliminating V, since the question doesn't ask for V. So you can do that. You can also look at the answer that's posted. All right, part C, it says the catcher is now modified to catch the still ball with a spring-loaded assembly identical. Okay, when the spring-loaded assembly start the ball and lock the ball in position. How does the height that the ball catcher assembly now rises to compare to the height calculated in A? So this question is asked to kind of have you think through the derivation that you did here. So I guess this is actually a good thing to realize or recognize, this going from step 1 to 2. So I said before doing any of this here that the energy is not conserved. But when you look at it carefully, we don't actually need to make that determination. We can just stay silent on whether the energy is conserved or not, and simply recognize what is conserved and say, well, momentum is conserved. And once you've said that momentum is conserved, then regardless of anything else happening, that allows you to write down this equation. And once you've written this down, then I hope you can see that, oh, I have one unknown, V, in terms of everything else that's known. So I can simply solve this for V. And I'm not going to do that here, but you can write down what V is. So this is step 1 to 2. Didn't actually need me to say anything about what happens to energy. So as far as this step from 1 to 2 is concerned, the fact that now the catcher is somehow modified in a sophisticated way to try to conserve mechanical energy doesn't really matter. So as the ball interacts with this new catcher, momentum is still going to be conserved, since this spring is just another source of internal force, not external force. So nothing that we did here changes. So you are going to get the same. So you are going to get the same speed V after the ball is caught in the spring. So the ball will push the spring down and eventually end up somewhere here. And with the ball in that position, the whole thing is going to be moving at some speed V. And what I'm saying is V here is same as V in B. So the very first step in part B doesn't change. Then it's not asking for what the V is, it's asking for how does the height that the ball catcher assembly now rises compares. And as you look at this from here, so as imagine it, and imagine the assembly moving from here up to some height. I hope you realize there also that it doesn't matter if there is a compressed spring in here or not. For the purpose of this motion here, we are really treating this whole thing as one single object with a mass small m plus big M. So that the fact that there's spring compressed in there, we don't care. So if it has the same starting speed V, then it has the same kinetic energy as before, which means after it rises to some height h, it's going to have same potential energy. So that means height h will be same as h in B. So really nothing changes. The only thing is some of the mechanical energy is conserved into the spring potential energy, but I guess spring potential energy doesn't do anything. So at least not here. So okay, so mechanical energy is conserved, but it doesn't have any effect on what you will see with the how high the catcher should rise. So by the way, in the detailed solution, you should see more lengthy description than what I have here. If this is all you write on the exam, then you're going to lose some points. All right, so it says, even though the spring in the catcher is identical to the launcher, when the compression of the spring in the launcher is compared to the explain why and find the expression that compares the okay, it's a very complicated question, and you should read the answer that's posted. I'll just point out the key main kind of concept idea here. It has to do with accounting for all the buckets of energy. So let's look at these two snapshots. One where I have the ball moving at speed of V naught. It's about to enter the catcher and be captured here. So it has the total energy here I'll call it initial. It's just the kinetic energy that the ball has. So it'll be 1/2 mv naught squared. Now, when you look at the, so this is a snapshot, initial snapshot. When you look at the final snapshot, after the ball has collided with the catcher, and now the spring is compressed, and the ball is caught here. If you were to write down your final energy is equal to just the potential energy, and say that should be equal to 1/2 k delta x squared or delta x final squared, and go back here, realize that this kinetic energy comes from the spring potential energy that we talked about in part A earlier, and say that this is 1/2 m delta x squared, and you try to set these two equal to each other and say that delta x final is equal to delta x, then you will run into a problem. And the problem you run into is that it's the question of it's the same first question that I mentioned earlier. That's the very first question that you should be asking for every conservation question over and over. It's to identify which quantities are conserved. So the question you should be asking is, which quantities are conserved in these interactions? So, okay, energy is conserved. That was the whole point of adding this spring. But what you should keep remembering from part B and C is that momentum is also conserved. So this initial snapshot represents the initial momentum of mv naught. So after the collision, after the ball is here, the final momentum, it cannot be zero, because if it's zero, then momentum isn't conserved, we are in trouble. So what the final momentum has to be is equal to, all right, some mass m plus big M moving at some speed v. And you say these two are now equal to each other. And once you admit to that, then you can go back and look at this expression here, the final energy. It's not just going to be the final potential energy. There is also going to be the final kinetic energy as given by this velocity v. And when you do the calculation, it'll be less than the kinetic energy that we was starting out from. So so that's why this spring gets compressed a little bit at all. But so this is the key fact that needs to come out in your analysis, that in order to conserve momentum in this collision, even though you are conserving all the mechanical energy, it should still happen in a way that some of this kinetic energy does remain as kinetic energy. So so the amount that spring is compressed, this is not going to be the same as the amount that the other spring was compressed. So I gave people lots of space here because this is an analysis that takes a bit of time, and look at the detailed answer for detailed analysis here.